Leetcode 124, binary tree maximum path sum. We will have trees, special case of trees, binary trees which have nodes that can have at most 2 children. And we want to find a path, very common scenario for dealing with trees or graphs, meaning a collection of nodes, and we want to have it optimized in such a way that we will have a maximum sum along this path, or the highest possible sum, and the sum is of course the sum of integers which are stored in those circles which represents our nodes, and we don't jump from any node to any other node. We just go through the connections which are visualized here as those straight lines, even though here we have a case of a directed graph, since each tree is a directed graph where we go from top to bottom, since the parent knows about the children, but the children don't know about the parent. But in the end, we will have a path which we don't care about the order, meaning that we will not need to reproduce the way in which the path is organized or which node we visited first and so on, nothing like this. But this could be a case since it's a hard problem. And of course, there are certain Leetcode style problems where we have to track each visited node and the order in which we visited them. But in this case, it's like an easier version of a hard problem where we just care about the sum itself. So in the end, we just return a single integer, nothing else. And that's it. So it is classified as hard since certain cases are not that obvious, but could be much harder. And so definitely when it comes to trees and graphs, there are very complicated problems related to those topics, and this one is not one of those. And the description is as follows. A path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them. And so that's this thing that I was telling you about. You cannot jump from one node to another. Only we go through those straight lines, meaning we even go just in one direction from parent to child, but this adjacent nodes having an edge connecting them, and meaning that we will just have to go through those connections and cannot jump whenever we want or wherever we want. A node can only appear in the sequence at most once. So that's another thing you cannot repeat. That's, I think, quite obvious, but it's stated nonetheless. So if we visited a node once, we cannot revisit it. Otherwise, it wouldn't be a path. And note that the path does not need to pass through the root. And this is also important information. Usually when we deal with tree-related problems, we always include the root and then start there and do something from the root. In this case, we'll also start from the root. Of course, we have to, since it's our only input, but the value that is stored there doesn't have to be included in the final sum. And so we can have a situation or a scenario where the root itself, and I think this is even a second example, stores a number which is not really it's not our best bet to take it, and we will simply remove it or disregard it in the final result. So the final result doesn't have to include the root at all. The path sum of a path is the sum of the nodes values in the path. Okay, so path 3 times. The path sum of a path is the sum of the nodes values in the path. Very complicated, but that's the thing that we have already mentioned, I think. Given the root of a binary tree, that's our input, return the maximum path of any non-empty path. And so another constraint, the path has to be non-empty. So at least one node has to be included. And that's the first example. All numbers are positive, meaning we can take every single node. That's an easy case. So we take 1, 2, and 3. That's it. And the second case, more complicated. There is a negative number, as we said, and this negative number appears at the root. And in this case, our best option is to take this right bottom subtree with 20, 15, and 7. And this will be the best possible root. And we will try to investigate this scenario a little bit deeper. Okay, so let's draw it. -10, 7, 20, 15, and 9, I think. -10. Sorry, here 9, here 7. 7 doesn't really matter, but to be to not confuse you and to be consistent, let's do it the same way. It is an example, and our best possible path goes through those nodes 20, 15, and 7. And so now is the question, how can we figure it out in the code using some kind of algorithm, and how can we do it in the most optimal way? And of course, we have to what? We have to traverse the tree. There is no other way to figure out what node values there are and what nodes at all we have. We have to traverse it in some way, and of course, the two strategies which are available to us are DFS and BFS. And I say, of course, since it's a hard problem, and I assume that if you are dealing with hard Leetcode problems, you have solved by this time multiple mediums, and you are very familiar with all those strategies, so I don't need to explain them like in details from scratch, just how they apply in this particular case. So here, at least for me, I don't see any viable option in which we can apply the BFS, since BFS goes layer by layer, and we want to construct paths. We want to construct paths from the nodes which are next to each other, which are connected, as we have already mentioned. And the only way I can see we could use BFS is first to collect all the nodes. Yeah, we could traverse the whole tree using BFS. And then on this node collection, go again through it and try to figure out the best path. And I don't think that it's really an efficient way. So maybe there is a way using BFS. You can hit me up in the comments and explain how you would do it. But for me, I think the DFS in this case, since we want to have those paths, is a clear winner. And the DFS will go as deep as possible. And we have, of course, multiple ways in which we can implement the DFS, and multiple ways in multiple different dimensions. So one way is, of course, recursive versus iterative. But what I meant just a second ago is that we can decide whether we want to explore the left side first or the right side first. Both would be a DFS compatible. But in the case of this tree, it's not a binary search tree. The numbers or the integers stored at nodes are not ordered in any way, or it's not guaranteed that they will be ordered, so we don't really care. We could go in any direction. We just need to implement a DFS in any way, which will go as deep as possible, reach a leaf, and then backtrack one level above and try to go in the other direction, creating a path. And of course, by creating this path, we will have to store the alongside this traversal the best value for the path that we have found so far. So Let's mark it with orange. The DFS will be our winner here. And now what we will do, we will explore both left and right node or the whole subtree. Since DFS in its recursive version will go till the very end. And of course, we can do a similar thing in iterative, but already I can do a small spoiler, and we will in this video explore just recursive version. Yeah, so we'll explore both left and right subtree and get the results from them. Store the results, and then we will do two things. We need to have some additional variable to store best result found so far. And this comes even before the exploration. So let's move it this to the left. This is here. This might be our very first point. We will have some way of storing the best result found so far, the path or the maximum sum along our path. Then we explore both left and right subtree as deep as possible. We get the results, and we do two things with those results. The first thing is compare if the path created by the current node and both subtrees, and here this is the hard part, or maybe part that's not really obvious at the first glance, yeah, that both subtrees together with the nodes create a better path. Compare the path created by the current node and both subtrees is better, maybe it is simpler, than the current best. And that's the first thing that we do. And the second thing is return the maybe better send the current value upward, and here we choose a better path from left versus right. And so why here we choose both and here we choose single, I think will be clear in a second, where we'll explore this particular example. Let's move it a little bit to the bottom so it stays with us. And let me zoom out, and we'll try to do all of this. This is the whole algorithm in like high level. And now let's try to solve this problem one by one using those steps. And I hope that everything will be clear by the end. So we will have the value from the left subtree, the value from the right subtree, or maybe even first, the current node, left, right, then this value, which is current node plus left plus right. Then we will have the value that we send upward, which is current node plus maximum between left and right. And finally, we have that global result that we store the best so far. And those are all the values that will be used throughout our solution. And let's make it a little bit bigger, and table like this, and code will be the first node. Well, if we go to the left, if we choose using our TFS that the first side that we explore is the left side, then from -10 we go to 9, and from 9 there is no other node. And so the first node that we will see will be 9. Then what will be the value that its left subtree returns? It doesn't have anything here, so it has to be 0. What will be the value that its right subtree returns? Again, 0. Then what will be this value? N plus L plus R. It will be 9 plus 0 plus 0, which is 9. And what will be this value? This value will be 9 plus maximum between 0 and 0. And finally, the best value is compared from the best that we had gathered so far, which at the moment is nothing, which we'll have to initialize with some value that is lower than the lowest possible. And in our case, it goes from -1000 to 1000, so it could be like -1001, or minus infinity in theory. But at this point, it's the first node that we explore. It has some impossible to reach small value. Yeah, so of course, the first one will get updated here. So at this point, the best one that we have seen so far is this path, which includes a single node. And that's the whole path that we have. Then we have the second node. So where will we go as deep as possible next? Well, the as deep as possible could be 15. And by the way, was it 15 and 7 in this order? 15 and 7. So let's make 15 here. Or we can just copy this, since it will be almost identical for 15. Of course, here there are no left and right subtrees, so we end up in a similar scenario. And here, by the way, the result is 9, of course, and the result is 15. And 9 was our previous best, but 15 of course is better. Yeah, so the new path that we have includes just this node, 15. That's it. Then we will have, let's copy from here again, 7, the next node that we explore. So we backtrack to 20 and try to go as deep as possible until we reach 7. And 7 plus 0 plus 0, 7, 7, 7. And the best value that we have seen so far is what? Is 15. Here we didn't see anything better than 15. So now we backtrack again to 20. And here finally we see something interesting. So let's make it longer. And 20 has both left and right subtrees. The left subtree returned 15 from here. And this is the value that we sent upward. And the right subtree returned 7. So now we have 20 plus 15 plus 7, which is what? 35, 42. Now we have 20 plus maximum between 15 and 7. Which is 20 plus what? Plus 15, 35. And the best value that we have seen so far is 42, which includes 15, 7, and 20. Yeah, and if you're worried about this part, why can we add both the left and right subtree? It's only because we update the best complete path. Yeah, here we send the value upwards, so we choose either the path going from the left or the path going from the right. But the best complete path includes the current node, and we of course can go in both directions. Yeah? That is the full path that we have. So the next node, the last one, is -10. And from the left, we have 9. From the right, we have 42. And now we have -10 plus 9 plus 42, which is 41. And the 41 is not better than 42, so 42 still stays the same. And then there is -10 plus the maximum between 9 and 42. Which is 42 minus 10, which is 32. Yeah, that's it. That's the complete solution. And here we have our final result. Maybe let's give the background like this. Can we send it to the bottom? Yes, we can. Yeah, here is the final solution. That's it. Now we have to convert it to Python, but I hope that this table helped you understand how it works. So we store some global variable for the best, which we initialize with the worst possible case. Yeah, so the nodes go from -1000 to 1000. So theoretically, it should be less than, but -1001 will be just for a single node. So I think we can just use, to be safe, -infinity. Now let's implement the DFS, where we will provide a single node and we will call the DFS on the root and then return the cell passed. And here, of course, the first case is always the edge case. So if not node, then return 0. And if we reach the end, the very bottom of the tree, then we return 0 for that. Otherwise, we want to have the values of our left subtrees and right subtrees. And why do I use this max here? Because if this value here is already negative, if you have a negative path, we can disregard it, since we want a path that is at least has something positive inside. At least one value which is non-negative. So we can completely disregard it. If it's already negative, then we make it 0. And otherwise, we want to update our best. If it's better, if the current value, node value, is better plus left plus right than what we have stored in the best so far. So this is this part. And the last part is return self. Not self, node value plus the maximum between left and right. That's it. That's the whole story. Now let's run. Accepted. And the runtime is a bit slow, but let's retry it. And now it's better. And have to subscribe to premium or wait a little bit to retry again. And now 70%. Yeah. So as you can see, the test cases again, which is a very common case, are not properly prepared, and the same result can get very different. Not the same result. The same code can produce very different results here, depending on your luck. Yeah, which is a common case for Leetcode test cases when they don't prepare enough of them or not varied enough. And in this case, you can have very different results. Or the other thing that might influence it is simply how overloaded their servers are at this particular time. And of course, if there are more things running in parallel, then the same code will run slower. So don't always get disappointed if your result is not at the top here, because maybe it's just on the Leetcode side, not on your side. Let's run it again, since I ran it once before and got I think this first time I got like 99%. So that's the Leetcode test cases for you.